Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Izzatie binti Halil. I am from Bachelor of Science Honor Applied Chemistry UiTM Perlis. My project is under supervision Dr. Faiezah binti Hashim. According to Rahman and Miller 2017, universal demand for plastic that led by the use of petroleum-based plastic material has increased and added stress to the existing management. As you can see in the video before this, plastic waste can be threatening to environment, human and animals. Low-density polyethylene, LDPE, known as type of thermoplastic polymer that used most commonly in various applications such as bottle, toys, and packaging material. LDPE is selected due to immune to biological degradation such as hydrophobicity, high tensile strength, lack of functional group, and long carbon chain. Starch is a native polymer that is an affordable, adaptable, and accessible substance that kept as granule in some plants. With increasing chitosan concentration in starch composite films, the strength of the tensile strength increases. Maleic anhydride grafted polyethylene (PEGMA) has been introduced as compatibilizer for the preparation of environmentally friendly LDPE TPS film as well as improved phase integration. A widely known compatibilizer that used to reduce the dispersed phase size, enhance the mechanical properties, and encourage interfacial addition is polyethylene grafted maleic anhydride (PEGMA). This study aims to prepare a series of LDPE TPS films with the presence of PEGMA as a compatibilizer and to review their tensile properties and thermal properties of the films. The research interest in developing bioplastic material has evolved rapidly to resolve petroleum-based plastic issue. However, LDPE also has limitations such as high thermal expansion, poor weather resistance, and non-degradation. Another limitation of LDPE is poor adhesive properties due to its inner surface, non-porous, and hydrophobic surface. Thus, starch was introduced to overcome the limitation of LDPE, particularly in degradation properties. The combination of LDPE and TPS, thermoplastic starch, is very attractive due to the good characteristic of both components. However, the properties of films and the performance also depend on other factors such as interfacial compatibility between the component miscibility, and properties of individual components. One of the limitations of LDPE TPS is poor addition between the filler and matrix. If physical massive amounts were applied to the LDPE TPS films, the addition of the film prevented loading forces from spreading evenly. By adding a commercial available compatibilizer, PEGMA, the miscibility between granular starch and LDPE will improve and will encourage interface addition in LDPE TPS. Therefore, this study presents a piece of new knowledge and future development of the tensile and thermal properties of LDPE TPS films and effect as PEGMA as compatibilizer. Bioplastic can save on fossil resources and GHG emission, while agricultural biomass production may cause adverse environmental effects such as soil erosion, soil and surface water eutrophication, or habitat fragmentation. In this review, Starch works with LDPE to produce bioplastic instead of synthetic plastic in everyday life. By using starch helps to reduce the environmental burden and improve the reuse efficiency of the material. This paper aims to review the current state of understanding on the characteristics and properties of low-density polyethylene and the thermoplastic starch. The precise aim of this study includes first is to review the effect of starch and compatibilization effect by PEGMA on the tensile properties of LDPE TPS films. Secondly is to review the effect of starch and compatibilization effect by PEGMA on the thermal properties of the LDPE TPS films. A previous study by Amin et 2019 on starch bioplasty show OH stretching. There is also a small peak that represents the stretching of C double bond O. Meanwhile, the presence of carbonyl group in the starch bioplasty also occurs. Stretching of CH is also observed, while the bands from 704.27 to 1014.48 per centimeter are matched to the CO bond stretching. According to data, Mato et 2019, to measure the effect of this biophilia of the mechanical properties of the produced film, different starch composition were blended with LDPE. Tensile strength decreased from 13.255 MPa to 4.021 MPa as starch content increased from 20% to 60% as shown in figure. The non-uniformity created by the hydrophobic starch and hydrophilic LDPE result in low interfacial addition of the two polymers, resulting in low binding of the molecule, which is exacerbated as the starch content in the matrix increase. The elongation at break was 14.78 mm for the sample containing only LDPE, while 1.88 mm for the blends only contain 60% starch. The high porosity generated in the structure reduced the ability of the blended films to lengthen when stretched at a constant load, resulting in rupture after a slight elongation. According to Zaman and Beck 2021, they analyzed the thermal properties of LDPE TPS, which is LPTS composite. In this figure, DSC endotherms reveal very slight change in the crystalline form of the matrix, indicating that melting temperature, which is TM in this study, was temperature dependent on compatibilizer and plasticizer. The TM of native LDPE, LPTS, LPTSMA, and LPTSDM range from 133.91 to 136.23 degrees Celsius. TM transmitted to higher temperature of the polymer when compared to native LDPE, with LPTSDM composite having the highest TM. In the formation of glycerin with starch and LDPE, the hydroxide group can form hydrogen bonds. Glycerin and the plasticizer in TMs has the compatibility to interact with LDPE and starch. The table showed that the LDPE and LPTS heat of fusion values were 103.25 and 105.67 respectively. As a conclusion, this review demonstrates the starch from tapioca, banana peel, maize, wheat, and potato can be considered as incorporated into LDPE successfully. The elongation at break and tensile strength of the LDPE starch blends declined when the content of starch was improved, owing to the uneven distribution of the starch in the LDPE matrix and in the incompatibility with LDPE and starch, which resulted in a considerable stress concentration. The addition of PEGMA to the starch with LDPE blends enhanced the tensile properties and elongation at break. This is because the addition of PEGMA enhanced the interfacial addition, which enhanced the tensile strength of starch with LDPE blends. With increasing starch content, the melting temperature of LDPE in the blend increases. In general, the thermal stability is improved with the existing of starch. There are still gaps that can be filled in order to furnish more dependable and widely tolerable materials. All of these aspects should be given more thought and consideration in order to obtain better findings and results. As such, recommendation of future works are: firstly is a study on the effect of starch and compatibility effect by PEGMA on the biodegradation properties of LDPE TPS film by using biodegradability tests. Secondly is a morphology study on the effect of starch and compatibility effects by PEGMA of LDPE TPS film by using scanning electron microscope. And last but not least is a study on the effect of starch and compatibility effect by the PEGMA on the flow properties of LDPE TPS film, which are map flow index and viscosity measurement.